Welcome to this video on DGPS, or Differential Global Positioning System. In this video, we will learn what DGPS is, how it works, and its applications in land surveying. Let's begin. Let's take a quick look at what we will cover in this session. First, we will understand why standalone GPS has limitations and what causes positioning errors. Next, we will learn what DGPS is and the basic idea behind differential correction. Then, we will understand the working principle of DGPS, including the role of the base station, correction signal, and rover receiver. After that, we will look at the key components of a DGPS system. We will also learn about PDOP, or positional dilution of precision, and how satellite geometry affects the quality of our observations. Finally, we will discuss cores and the practical applications of DGPS in cadastral and land record surveying. Let us start with the basic problem.
A standalone GPS receiver determines its position by receiving signals from satellites. However, the position calculated by the receiver is affected by several sources of error. The first is satellite clock and orbit error. Even very small inaccuracies in satellite timing or the predicted satellite position can affect the final coordinate. The second is atmospheric delay. As satellite signals travel through the ionosphere and troposphere, their speed and path can be affected. Another important source is multipath interference. This happens when satellite signals reflect from buildings, trees, terrain, or other surfaces before reaching the receiver. Finally, receiver noise and poor satellite geometry can also reduce the quality of the position. Because of these factors, a standalone handheld GPS may typically have a positional error of around 5 to 10 meters, as presented in this training material. For general navigation, this may be acceptable, but in land surveying, even a few meters of error can be significant. For example, it may affect the location of a boundary pillar or a plot corner. This is the problem that DGPS is designed to reduce.
So, what exactly is DGPS? DGPS stands for Differential Global Positioning System. It improves GPS accuracy by using a fixed base station at a known location. The base station calculates the positioning error and sends corrections to the rover receiver, helping it determine a more accurate position. In simple terms, the base calculates the error and the rover uses the correction. Now let us understand the working principle of DGPS. Both the base station and the rover receive signals from the same GNSS satellites. Because the two receivers are located relatively close to each other, many of the errors affecting the satellite signals are also similar at both locations. The base station is installed at a point whose coordinates are already accurately known. It compares its known position with the position calculated from the satellite signals and determines the error. This correction information is then transmitted to the rover through a communication link. The rover receives the correction and applies it to its own position calculation. The important principle here is that the base and rover experience almost the same atmospheric conditions and satellite-related errors. Therefore, the correction calculated at the base can significantly reduce common errors at the rover. This is the fundamental idea behind differential positioning.
A typical DGPS setup consists of three major components. The first component is the reference, or base station. The base station is a stationary receiver installed on a point with precisely known coordinates. It continuously observes satellite signals and calculates the positioning error. The second component is the DGPS rover receiver. The rover is the mobile receiver used by the surveyor in the field. It is taken to locations such as boundary pillars, DAG corners, or other survey points. The rover receives the correction information and uses it to improve its position. The third component is the communication link. This is the channel through which correction information travels from the base station to the rover. Depending on the system, this communication may use radio, GSM, or internet-based communication, or satellite-based broadcasts. So we can remember the three main components as base, communication link, rover. Let us now look at the DGPS process step by step. Step 1. Track. First, the base station tracks the same satellites that are being observed by nearby rover receivers. Because the coordinates of the base station are already known, it can determine how much error is present in the GPS-derived position. Step 2. Compute. The base station compares its known surveyed coordinates with the position calculated from the satellite signals. From this comparison, it calculates the positioning error. Step 3. Broadcast. The calculated correction is then transmitted continuously to the rover. The correction may be transmitted in a standard format, such as RTCM. Step 4. Apply. The rover receives the correction information and applies it to its own GPS observations while working in the field. Step 5. Refine.
Accuracy depends not only on correction, but also on satellite geometry. This is where PDOP, or positional dilution of precision, becomes important. PDOP tells us how well the visible satellites are distributed across the sky. Good satellite geometry gives better positioning, while poorly distributed satellites can reduce accuracy. A PDOP below 2 is excellent, 2 to 5 is good, 5 to 10 is fair, and above 10 is poor. Therefore, before taking important field observations, always check the PDOP value, and if necessary, wait for better satellite geometry. Now, let us see the main advantage of using DGPS. A standard standalone GPS position may typically have an error of around 5 to 10 meters. With DGPS correction, the accuracy presented in this training material improves to approximately 1 to 2 meters. That means the positioning becomes significantly tighter and more useful for field surveying. For land record work, this improvement can make a major difference. A position within approximately 1 to 2 meters can support activities such as boundary verification, ground control point support, and DAG level positioning, including field activities. So DGPS reduces the uncertainty in the position and provides a much more reliable coordinate for field operations. Let us now summarize the major advantages of DGPS. The first advantage is improved accuracy. Compared with a standalone GPS receiver, DGPS provides significantly better positioning accuracy, with the training material indicating approximately 1 to 2 meters under suitable conditions. The second advantage is real-time correction. Instead of waiting until the survey is completed for correction and processing, the position can be refined while working in the field. The third advantage is greater reliability. Differential correction helps reduce the effect of common positioning errors, including atmospheric effects. The fourth advantage is consistent results. When the same point is observed under suitable conditions, repeated observations can provide closely matching positions. Therefore, DGPS is not simply about getting a coordinate. It is about obtaining a more accurate, reliable, and consistent position for field surveying. Let us now look at some key applications of DGPS in cadastral and land record work. First, boundary and DAG verification. DGPS helps locate and verify plot corners and boundaries accurately. Second, ground control point establishment, which supports the georeferencing of cadastral maps and spatial data. Third, survey and resurvey initiatives, where DGPS supports accurate field-level positioning. Finally, QA/QC of survey data, helping cross-check and improve the quality of survey coordinates. Overall, DGPS helps ensure more accurate and reliable land record data. Let us quickly recap what we have learned in this session. First, DGPS improves the accuracy of standalone GPS by using a fixed reference station at a known position. Second, DGPS provides significantly better positioning. Third, survey and resurvey initiatives help improve the quality of survey coordinates. Finally, QA/QC of survey data, helping cross-check and improve the quality of survey coordinates. Overall, DGPS helps ensure more accurate and reliable land record data. Let us quickly recap what we have learned in this session. First, DGPS improves the accuracy of standalone GPS
Second, the base station calculates the positioning error and sends the correction to the rover through a communication system, such as radio, GSM, or internet-based communication system. Third, according to the values presented in this training material, positioning accuracy can improve from approximately 5 to 10 meters with standard GPS to around 1 to 2 meters with DGPS correction. Fourth, CORS networks extend the same principle across a wider region, allowing surveyors to obtain correction services without establishing their own base station. And finally, DGPS has important applications in cadastral surveying, boundary verification, ground control point establishment, survey data QA/QC. The key message to remember is simple. Better correction leads to better positioning, and better positioning leads to more reliable field survey data. Thank you for watching this video on Differential Global Positioning System, or DGPS. For more videos on surveying, GIS, and land governance, stay connected with the Center of Excellence on Land Governance Guwahati Center and Assam Survey and Settlement Training Center. Thank you.